Okay, we're starting. Let's quickly run through the quiz as a review. So this is quiz 7. A was this matrix 3, 2, minus 1, 2, 2, minus 1, 0, minus 1, 1. Okay, first one was to compute the determinant of A. What did you do?
The bottom last row.
Huh? Did you do any row operations, or you just went directly into it?
One direction.
You could have done a row operation. This is also going to be the same as, let's say I took, what?
And then you get a whole bunch of.
Yeah, if I say something like row 1 minus row 2, that's a type 3 operation because row 1 didn't change, and I'm adding to it a multiple of another one. So that's this minus this, 1, this minus this, 0, this minus this, 0. Leave everyone else the same, that's the same determinant. And then I could go along row 1, but of course you didn't have to do that, that would be a plus sign. So this ends up being just the determinant of 2 minus 1 minus 1, 1. That's going to be 2 minus 1, that's 1. A inverse. How did you find A inverse? Who did the adjoint method? Okay, let's do both. So let's do the adjoint method. What's the formula that you use there?
1 over the determinant.
A inverse is 1 over the determinant of A
Multiplied by the adjoint.
multiplied by the adjoint of A. And the adjoint of A is what?
It would be the cofactors.
The transpose of the cofactor matrix. So this is the matrix Cij transpose, where big C is the cofactor. So in this case, that would be 1 over 1 times something transposed, and then remember we have that whole checkerboard of signs going, so that's plus, minus, plus, minus, plus, minus, plus, minus, plus. And so now we just start to enter the numbers. So we go to the original matrix and we're going to find all these mini determinants. So to replace the 3, we're going to replace it by its cofactor, which is 2 minus 1. So 1. To replace the 2, replace it with its cofactor, 2 minus 0, 2. To replace the minus 1, replace it with its cofactor, that's minus 2. To replace this 2, replace that with its cofactor, that's 2 minus 1. To replace this guy, replace that with that cofactor, that's 3. Replace this guy with his cofactor, that's minus 3. Replace the 0 with that cofactor, that's just 0. Replace this guy with his cofactor, that's minus 3 plus 2. Right? So it's minus 1. And finally, replace this one with his cofactor, and that's going to be 6 minus 4, that's 2. So you apply the signs and take the transpose, and so the first row becomes the first column.
Minus 2, negative 2.
Where? Negative. Okay. This one, so that's minus 1, positive 3, positive 3. And then in the last one we have 0, positive 1, positive 2. So that would be the A inverse. Is that the answer? Let's check to make sure we didn't make a mistake. I think I gave you guys enough time to actually check that. So let's do 3, 2, minus 1, 2, 2, minus 1, 0, minus 1, 1. So here I'm doing the check. How can I check is if I multiply these two, I should get the 3 by 3 identity. So this would be 3 minus 4 plus 2. The middle one would be minus 3 plus 6 minus 3. This would be 0 plus 2 minus 2. This would be 2 minus 4 plus 2. This would be minus 2 plus 6 minus 3. This would be 0 plus 2 minus 2. And this would be last row 0 plus 2 minus 2, 0 minus 3 plus 3, and 0 minus 1 plus 2. So that's 1, 0, 0, 0, 6 minus 5 is 1, 0, 0, 0, 1. Right, so that's the right answer. Right? So at this point, if you made a mistake, then you know to go back and check something. And you'd realize that maybe you forgot the checkerboard of signs like Jackie did, or something else. Okay, so that was one method, the adjoint method. So you put 1 over the determinant, which I asked you to find in part A, so it was more than about a viable method to use here. And you replace each individual number in the original by its cofactor, meaning you block out everyone in the current row and current column of that number and find the determinant of the remaining part. Apply the checkerboard of signs, and then once you take the transpose of that, that gives you the inverse. The other method would be row reduction. So we can say, so if that was your preferred method, A inverse by row reduction. So this is just another way to do problem 1B. So you can start with the original matrix. Augment it with the identity. And find the reducer echelon form. So let's get a 1 in the top left. So I can take row 1 minus row 2. This minus this is 1, this minus this is 0, this minus this is 0, this minus this is 1, this minus this is minus 1, this minus this is 0. And now I immediately want to kill that 2. So let's take row 2 minus 2 times this new row that I just created. So this minus 2 times that, 0. This minus 2 times that, 2. This minus 2 times that, minus 1. This minus 2 times that, minus 2. This minus 2 times that, that's 3. This minus 2 times that, that's 0. Now let's immediately try to get this guy to die. So what can I do here?
We're switching. Add row 3.
Or I can just say row 2 plus 2 row 3, right?
Wait.
So this plus 2 times that, 0. This plus 2 times that, 0. This plus 2 times that, 1. This plus 2 times that. This plus 2 times that. This plus 2 times that, 2. Then I can just add these two and then divide through by 2 and we're done. we sort of know what answer we should get to, so it's not going to be the check again. And so
Add row 2.
just add these two guys. Just 1, 0, 0, 1, minus 1, 0. I'm going to take row 2 plus row 3. Leave the last row. If I add these two, I would get 0, 2, 0, minus 4, 6, 2. So one last step. Not being super efficient here. I remember when I quickly did the solutions last night, I actually did this in like 1 or 2 less steps, but whatever, we get there. Wasn't too bad. Was that what we got? I mean, you did it this way, you could have checked afterwards. Okay, so part C. This was something I mentioned doing the inverse, but I don't think I ever actually did an example. So we'll let this serve as the example. Using the inverse of a matrix to solve a system. So if I have 3x plus 2y minus z equals 1, 2x plus 2y minus z also equals 1, minus y plus z equals 0, and I want you to solve the system. What you should have noticed here is that the coefficient matrix is A from above, right? So the coefficient matrix of that, if you look just at the coefficients, the 3, 2, minus 1, 2, 2, minus 1, 0, minus 1, 1, it's just this matrix here. And so now we're going to use the fact that if AX equals B and A inverse exists, then that means that I can solve for X by just multiplying both sides on the left by A inverse. And so the solution to this is just going to be that matrix times the right side, 1, 1, 0. So that's going to be your x, y, z. You write as a column vector, and that seems to be 1 minus 1, minus 2 plus 3, and minus 2 plus 3. So that's the answer here. And so that was one part C. Problem 2, what does it mean for A to be symmetric? Huh? A equals A transpose, so that's all you have to write there. So that was problem 2. That means A is equal to its transpose. Talk about the bonus, even though we're going to talk about, at this point I'm not sure I'll make it to subspaces, but I'll talk about examples of vector spaces. So I asked you to circle things that are not, which are the following are not properties of V, given that V is a vector space. So the guys in question were these guys. for each u such that u is not a zero vector in space, there exists a u inverse such that u times u inverse is equal to 1. So these were all properties here that I just listed that a set might have, where u, v are vectors, k and l are scalars. So which of those were not properties of a vector space?
First one?
The first one is not a property of a vector space. Any others? Yeah?
The last, yeah, for each u that's not zero.
The last one. The others are, right? So that's not really something you figure out. That's just a definition. So knowing what a vector space is just means you should know it's some definition that something fits to. And so that's what we're going to start now. So we're going to start chapter 4. This is a chapter on vector spaces. So we're going to start looking at the main objects of study for a linear algebra course. We're going to start with 4.1, where we just talk about vector spaces in general. I think they talk about real vector spaces. Not as opposed to fake vector spaces. Real just means the real numbers are the field that we're using. That's where we're getting our scalars from. I'll just give you a fuzzy definition because it's not going to be the point here. But a set is called a field if it is non-empty and has two operations defined on it: addition and multiplication. So that, and usually there are a list of properties here, but this is a fuzzy definition. I'm not going to tell you exactly what the list of properties is. But the set behaves like the real numbers. Right, so every kind of operation you can do with a real number, you can do with such a set. So that basically means addition is commutative and it's associative. And everyone has a negative. There's a zero vector. There's a multiplicative identity, which is called the 1. There's also multiplication is defined and it's commutative. And every non-zero element has an inverse. So these are properties of fields, not vector spaces. As well as a distributive law holds. So multiplication distributes over addition. Any set with two operations, addition and multiplication, that fulfill that set of axioms is called a field. The elements of fields are called scalars. By the way, examples of fields. The real numbers are a field. They're the quintessential example. Right, so R is a field. If you look at also the rational numbers, those are a field. Q is also a field. The complex numbers are also a field. And these are all examples. Something like Z mod 2, the integer is mod 2. So if you consider a set that describes the remainder after you divide by 2, the remainder of the integers after you divide by 2, you can either have a remainder of 0 or a remainder of 1 when you divide an integer by 2. And we can define addition on this set. So I can say something like 0 plus 0 is 0, I can define 1 plus 1 is 0. I can define 1 plus 0 is 1. I can define, and of course addition is commutative here. And I could define multiplication. 1 times 1 equals 1. 0 times 1 equals 0. So it turns out the set of these two elements with those operations for addition and multiplication will satisfy all the axioms of the real numbers. There's a notion of division in such a set, and so on and so forth. Fields aren't the important thing. If you want to study fields, you would do that in abstract algebra, but they are where we get our so-called scalars from.
Professor,
Yes.
how does that work? 0 plus 0, 0, right?
Like, how'd you get 1 plus 1 is 0? What do you mean by that?
Oh, probably the easiest, the most analogous thing you can think of is clock arithmetic. So you can talk about, for example, Z12. So just think about the numbers along a clock, right? Eventually, once you go past 12, if you add 1 to 12, you get back to 1, right? So it's like you can always go in a loop. But just now imagine a clock where there are literally only 2 points, right? Where once, if I take 1 and I add nothing, I stay here. If I take 1 and I add 1 revolution, I end up
Not 2, right?
here, right? So it's like I'm jumping between 1 and 2. It's just a clock with 2 parts on it. And so you can also think of it as just remainders. So if I add 1 plus 1, I get 2, right? Because 1 plus 1 is 2. If I add 1 plus 1, this is equal to 2. But the thing is, what is the remainder when you divide 2 by 2? Right? It's 0. Right? Or you can talk about 5 in this set. If I'm in Z mod 2, 5 is equivalent to what? It's actually equivalent to 1, right? Because if I divide 5 by 2, the remainder is 1. The number 7 would be also equivalent to 1. It's like I'm literally splitting all the integers into 2 groups. They're either odd or they're even based on whether their division is, based on whether their remainder when divided by 2 is 1 or 0. And so I can literally group all integers. So when I'm adding all these guys, if I get another number other than 1 or 0, I can reduce it to 1 or 0. And by such a notion, that set will actually behave like the real numbers, even though it only has 2 elements in it. I can divide, I can multiply, I can add. So some things that are not fields, some like the integers, these are not a field because division doesn't work, right? I can divide 2 integers and not get an integer back. So things like that are not fields. The natural numbers, also not a field, etc., right? Moving on. So now we can define vector spaces. Let V be a non-empty set. Let F represent a field. V is said to be a vector space over F if, so here's what makes something a vector space. There are 2 operations defined on V. Addition and scalar multiplication. such that the following hold. For any U, V, W in V and any K, L in the field. Right? So there are 10 things that make up a vector space. So if you have a set, you define two operations on it, multiplication, addition and scalar multiplication. It ends up being a vector space if the following hold. One, it's closed under addition. Meaning, if U and V are elements of V, then U plus V is an element of V. So if I add two elements in the set, I get another element in the set. That's called closure under addition. The other property is addition is commutative. That's just a fancy way of saying the order does not matter. That means that U plus V is the same as V plus U. It should not make a difference what order you add things in. 3. Addition is associative. This means if I'm adding more than a pair of things, it doesn't matter which pair I decide to add first, I will get the same answer. And this is working for any vectors in the set. I'll tell you what vectors soon, I guess. 4. There is the existence of a zero vector. There exists an element 0 called, and that's a notation, the zero vector. Such that, here's a definition of the zero vector. If you take U and you add it to 0, or if you take 0 and you add it to U, you get U. This is called the additive identity. So this is the existence of an additive identity. So this symbol, remember this symbol means there exists. I didn't talk about that since like lecture 1, so I'm going to remind you. Backwards E means there exists. Upside down A means for all, or for every. So for all U in V, there exists a minus U in V such that if I take U plus minus U, I get 0. Meaning the same element that was defined in property 4. 6. We have closure under scalar multiplication. That means if K is a member of the field, which is a scalar, and U is an element of V, then if I take K and I multiply by U, that is also an element of V. This here is called a scalar multiplication. I'm taking a scalar, which comes from the set F, multiplying a vector, which comes from the set V, to create a new element, and that element will also be an element in the set V. 7. Scalars distribute across vectors. So if I take K times U plus V, this is the same as KU plus KB. 8. It goes this way as well. The sum of scalars will distribute sum-wise. Nine. We have associativity of scalar multiplication, so this is the same as that. And finally, 10. If I take 1 times u, the result is u, where 1 is the multiplicative identity of f. Any set that has 2 such operations defined that obeys those 10 rules, we call it a vector space. I have to give you some notes on the definition here. So the intuition for this sort of comes from the set of vectors that you know from Calc 3, for example. You'll notice that the vectors in Calc 3 obey all these rules, and the notation is very suggestive of that. But I do want you to understand that it is far more general than that. These vectors can really be anything. They can be functions, they can be polynomials, they can be matrices. Matrices form a vector space, and so on and so forth. But anything that has these 10 properties, you'll notice that matrix addition obeys all these rules. You'll notice that the matrix with all entries 0 will obey the rules for the 0 vector. You'll notice that if you just take the negative of each component in a matrix, this rule will apply. Notice that if you take scalar multiplication of matrices, all these rules hold. So this can apply in general, not just to like vectors that you know from Calc 3. But the intuition is the same. You want to generalize the behavior of a set like Rn from Calc 3 and see what kind of other sets have this same sort of behavior. So notes on the definition. The elements of such a V are called vectors. Not the same as vectors in Calc 3, not the same as vectors in the sense of physics. Vectors as in any elements that follow these 10 rules. The elements of F are called scalars. Addition doesn't mean regular numerical addition like you know from the number line. It can also mean something very general. Addition just means a rule to combine 2 vectors to create another vector in some process. That depends on the context you're talking about at the time. When we talk about scalar multiplication, this is just a rule to combine a scalar and a vector to create another vector.
Professor?
Yes.
It says addition, right? Rule to combine 2 vectors to create another vector. So
Yes.
Like, is that like 2 dimension? If you use addition, then it becomes 3 dimension?
No. If I take 2 elements in the set and I apply some rule to them that make another element in the set in some predictable way for arbitrary elements, I call that operation an addition.
But the vectors are like in a dimensional sense, like 2 dimensions and 2 vectors.
If you're thinking of R2, you're thinking of R2 here?
Yeah, yeah. It's
then yeah, if I'm looking at R2 as an example, what do my vectors look like in R2? What do vectors in R2 look like? If I'm looking at R2. They just look like coordinates, right? Like A comma B is a vector in R2. So it could be 1 comma 2, 15 comma 17, could be whatever. But then, according to R2, I can add two vectors by doing this operation. I add their numerical components inside.
I was thinking about something else.
Right? And so this is a rule that combines two vectors to give me one other vector that lives in
It
R2.
increases the length of the dimension.
We have no notion of length here. That, in terms of a vector space, length is irrelevant. Right, but that's just a rule. But that didn't have to be the rule. That's just the rule that we use. That's the rule we use because it makes sense from a physics standpoint, and calculus is the mathematics of physical science. So that rule made sense. Yeah.
The scalar elements of F they have to be the same things that make up the vectors, right? Like
No, the scalars aren't. No, they don't.
Okay.
So another thing, I'll give you some examples of vector spaces later, but it can get quite arbitrary. It literally doesn't have to be this. What else do I want to mention? Notes on the definition. So addition and scalar multiplication should be taken to be very general, very arbitrary. They're just rules to combine things to create another thing. The rule depends on the context at the time. This rule is natural because in physics, that's how you would add two vectors. That actually makes sense. But it doesn't have to be. I can create an arbitrary rule that whatever I want. I could just say, you know what, I want A, B plus C, D to equal, take this component, add to this component, and then make the second component 0. I could just make that definition. Why? Because in the context I'm working at the time, it makes sense to do that. Whatever I'm trying to model would behave in a way that would cause me to define that, right? And so you would say to yourself, would that create a vector space if I force my addition to be that way? Right, we'll get to that soon, but I think I want to make some other notes on the definition. Okay, so the elements in F are called scalars. The elements in V are called vectors. Addition is a very arbitrary rule that combines two vectors to get another vector. Scalar multiplication is an arbitrary rule that combines a scalar and a vector to create another vector. What else do I want to say? Again, a vector space has at least one element. So there's no empty vector space. Namely, which element? The 0 vector. Which means, and why? This is by axiom 4. Axiom 4 posits that we do have an element that functions as 0. Meaning whatever rule I have for combining the vectors, that rule applied to this element will not change anything. Let's look at some examples. Oh, before that, something else I wanted to know. It's going to be important for us, because linear algebra is the study of vector spaces and the linear transformations on vector spaces, it's important for us to know when we're looking at a vector space from when we're not. Right? It's kind of just like how in calculus, it's often important for you to know, is this function continuous or is it not? Right? Can I do a derivative here or can I not? So that's going to come up. To identify, so there are some, because you have to check 10 rules, it can be sort of daunting if you're just starting out. But there is some rules that are easier to check than others. To identify a set with its operations as not a vector space. it's often, unless something else jumps out at you, it's often best to check these properties. Closure under addition. Closure under scalar multiplication.
Question, what's an axiom?
An axiom is a rule that we accept without proof. So it's just an assumption we accept without proof. And the existence of zero. Oftentimes when something fails to be a vector space, it's because of one of these things will fail, and they're also the easiest ones to check, so I would check those three easier. For example, I cannot look at the integers as a vector space over the real, as a vector space over the real numbers. Right? Example, Z is not a vector space. I don't know if this is going to show up, it looks very light, over R. Why? It has a zero vector.
It's not closed under
It is
division.
not zero.
Division we don't care about. Vector spaces don't have division. Scalar multiplication is a problem. So if I take any element, take n in Z, then if I take the square root of 2 times n, it's no longer in Z. So if I multiply by a scalar, it's not in the set anymore. Which means I cannot think of this as a vector space. Because if I look here, I'm talking about usual addition and scalar multiplication. Right? With usual addition and scalar multiplication, I cannot think of the integers as a vector space. They fail miserably. Right? The integers form something else called a ring. Again, that's not something we're going to do, that's abstract algebra. But it's not a vector space. I cannot think of the integers as a vector space. Because scalar multiplication doesn't work. I can easily get outside the set of integers. Let's look at some other examples. Let's say, example 2, a non-example. Let's say a color, I spelled it, color map based on the primary colors. Red, yellow, blue. Right? Where addition equals mixing let's say 1 gram of each color together. Scalar multiplication equals changing the quantity, scaling the quantity. Right? So let's say, like a computer, I assign a number to each color on a color map. Right? I get all these colors by mixing primary colors together. Can I think of points on that color map as a vector space? The answer is no. Why not? Right, so to obtain the point that's like green, which has this certain wavelength, I mix equal portions of what two colors?
Yellow and white.
I would mix 1 gram of blue with 1 gram of yellow to create the color green. Right, so I can get to any point on this color map by mixing these colors together. So if I think of those set as points as a set, and I think of addition as me mixing colors, scalar multiplication just describes the proportion of each color I'm adding. So let's say I want a really dark green, I add more blue than yellow and so on and so forth, right? If I make the operations on these colors, can I think of that set as a vector space? I claim the answer is no. Can you tell me what's wrong?
Green's
Yeah.
not in your set.
What?
Green is not in your set.
Well, I never said it's the entire set. I said based on.
Oh.
I'm talking about all colors that can be created from these things. This gets to the point of a basis, which is a few sections down. We'll talk about that. So a basis is the smallest set of vectors by which you can create every other vector in the set. So I'm calling this a basis of a color map. Why can I not think of this as a vector space? I'd probably start by checking with these.
Oh.
Yeah? Who's the zero color? Right? Moreover, how would a negative work? What does it mean to be the negative of blue? Right? I don't have a zero vector in this set. I don't have a negative color in this set. If I have blue, there's literally, even if I came up with a zero color, there's no guarantee that I can mix some paint with blue to get this non-color. Right? The absence of color. If I start with blue, I'm always going to have some color there, no matter what I start adding to it. Right? So it's not a vector space. Why? No zero. No negatives. Right? So that's not a vector space if I do that. So I cannot think of a color map on the computer as a vector space. Even though I can think of the points in R2 as a vector space, if I just prescribe this kind of operation on it, it's no longer a vector space. We're pretty much running out of examples. We'll do a lot more examples next time. Like R2 is a vector space, Rn, we'll talk about the complex numbers, the set of matrices, magic squares. We'll talk about a lot of examples. We'll play around with this idea of what makes a vector space, what makes something not a vector space next time. And we'll talk about subspaces. But the thing is, we're being very abstract here, very general. Don't be married to what the word addition means. Oh, that means you just add. No, it no longer means that. We'll pick up on Thursday.